Yeah, we'll probably start them, and then depending on how much we get done will depend on when we start the thing. Hey,
Hi, I was looking at your syllabus and it said you uploaded your videos in web courses.
they're
And I was
uploaded. Oh no, they're uploaded on YouTube.
Oh, okay.
Yeah,
Thank
they're
you.
all on YouTube.
Okay, I'll
Yeah,
find it later.
yeah, yeah.
Thank you.
All right. Hello, everyone. Yeah. So, logistics. Remember the AI assignment? I think I gave a slight extension on it, but make sure you all have done that. If you're like, what AI assignment? Remember, it's the one of using LLMs, AI, all that stuff to actually learn, not just spit out answers. Because that's often how it's utilized currently by the vast majority of people. You put stuff in, it spits out an answer, you're done. The purpose of the assignment was to help you all use it in a way that's for learning, i.e. a conversation with the thing. If you do one and done, you just put in the thing and spit out an answer. That's basically simply just Googling something, but you're not actually engaging with it, and learning requires engagement, yada, yada, yada. Explained it all before. Your all's test is not this Thursday, but next Thursday, November 6th. So to give you all, a few heads up on this. So the current plan is, I forget, like 24, 25 multiple choice questions. I think 25, because it goes into 60 nicely. So 25 multiple choice, like the last exam. And then my current plan is there'll be 5 for your response, and you'll pick 4 of them. Now, the difference here is that each of them only has 1 part. It's not like 4 with multiple parts. So last test, you all had effectively 6 problems, and you picked 4 of them. Was effectively kind of how it worked. By nature of me, like just making these all independent problems by themselves, 4 out of 5 feels kind of reasonable. So you pick your 4 favorite. And so the grading breakdown will basically be the same as the first test, specifically. Get out of here. Specifically, you're going to have 60% of the grade for the multiple choice, 40% from the free response, just based on the time spent on each section. That's kind of how I determine how the points are allocated. My lecture class, theirs will be very slightly different than yours, just for funsies. They're going to have 64% of theirs be multiple choice and 36 be the free response. But that's because they only have 3 free response instead of 4 free response. They also only get an hour and 15 minutes, and you all get 2 hours and 50 minutes. So, like, there's some more context here to all this. But in case you chat with anyone, you're like, why is ours different? It's based on the time I expect you kind of to spend on each section. And that varies because of logistics. So, great. The free response, one of them will be from each week. So one of them will be from DC circuits. One of them will be from forces on moving charges. Forces due to magnetic fields. So forces on moving charges / forces on the current carrying wire. One of them will be on magnetic fields due to current carrying wires. One of them will be from Faraday's law. That's what we're finishing up today. And then the last one is undecided. I haven't made that one. So I'll figure out what that last one's going to look like. Maybe some combination of a couple of them. That's probably what it's going to be. The last one will be something that uses a couple of the concepts together, just to make it fair, so that there's not an emphasis on one versus the other. We are not going to get to AC circuits in time for the test. There's no way, Jose, that we're going to have time for that. So what we will do is we'll do inductors, which are just solenoids. We're going to do inductors on Thursday. We're going to actually probably get to inductors today. And depending on how much of inductors we get through today, we might start the lab early on Thursday, because if I get through all of inductors today or most of it, there's nothing more for me to cover. So we'll just there's a potential that we might just start with the lab on Thursday, or we'll start the lab soon after, maybe after like 20, 30 minutes. We'll see. I honestly don't know the answer to that. But we don't really have much left in this PowerPoint, and inductors really shouldn't take a terrible amount of time. So Thursday's lab will hopefully be good. The goal of Thursday's lab, I haven't made it yet, but I tested it. You're going to use your phone again to measure magnetic fields, and we're going to find the distance dependence of the magnetic field due to a permanent magnet. So we're going to find whether or not it's 1 over r, 1 over r squared, exponential decay, 1 over r cubed, whatever. And you're actually going to collect the data and determine what equation fits best to it. So it'll be interesting. I tested it. It worked pretty well, as long as you're careful. And yeah, you'll see what I mean on Thursday. But it should be fun. Great. Okay. I think that's that. What's the joke?
What do you call a parade of rabbits hopping backwards? A receding hairline.
Yeah, it's good. Because hares are rabbits and they're going backwards. Yeah. Because I've made somewhat of a draft of your all's test, my goal is to make your all's review PowerPoint in the next few days. So that's a PowerPoint I'll go over next Tuesday during class. My goal is to make that in the next few days. By the latest, have that done by Friday so that you all have it over the weekend or whatever to look over. Just for that context. But otherwise, make sure you all can do the right-hand rules. My gosh, if you all can't do the right-hand rules, you're going to have a very miserable time. Somewhere between 30 to 40% of the problems require you to use right-hand rules in some capacity. Why? Because you all need to be able to visualize things in 3D space, and that's really what right-hand rules are doing. It sounds, yeah, it is a very important skill. The first right-hand rule is actually just figuring out the direction of a cross product. That is all right-hand rule number 1 is doing. It's a cross product between the velocity and the magnetic field. It applies to every cross product you ever learn, and you're going to learn more cross products. So the first right-hand rule I teach you, actually, that whole swinging door method, that applies to any cross product you ever learn in any class, ever. If you have two vectors that get cross product together, so for example, just if I have A cross B, what's the direction of C? You put your fingers in the direction of A, you swing them towards B. So in this case, A is to the right, swing my fingers towards B, which is up, C is out of the page. Any arbitrary vectors that gets cross product, the swinging door method is how you find the direction of the cross product. So anyway, hopefully I've convinced you it's important, but even if I haven't, it'll be 34% of the test. So make sure you all can do it. Make sure you practice them. Make sure you practice a bunch of problems intermingled together. People mix them up all the time. And there is no shortcuts to these, y'all. If there was an easier way, I'd teach it to you. This is the easy way. The hard way is doing it by math and actually doing a cross product. That's the long way. So, anywho, it's going to go great. We're going to have so much fun on test 2. Grand time. All right, so last class, we did a bunch of things, but we found that when you had a changing flux, it makes an EMF. EMF is just like voltage. And it makes this voltage, and if you have a voltage, you have a current. So that was kind of the emphasis. We went through and we did one where the magnetic field was, or this was the area was changing. We had one where the field was changing. This one is very important. We had one where the angle was changing. And I had to remind you all of some variables from rotation: angular velocity, angular frequency, and then regular frequency. These are very important things for you all to know because the world is full of periodic motion. Like, that's actually, so we're going to finish inductors this Thursday. I made an entire PowerPoint on AC circuits that we won't actually go through it all, which is very sad. I will still post it for you all, but we'll spend the last week and a half of class. So after y'all's test 2, we only have 4 class days after test 2. Just to show you all this visual stuff. Here's the test. It's November 6th. That Tuesday following it is Veterans Day. There's no class on Veterans Day. It's Tuesday, which is kind of funky. So we don't have class November 11th. And then we have the 13th. We have the 18th, we have the 20th, and then we have the 25th. So we have 4 days. 3 of those will be content. The 25th will just be reviewing everything. That's the week of Thanksgiving. So like we always do a review day before a test. This is the last class, is this November 25th. That's true of every single one of your classes. There's no classes on the 26th. No class on Wednesday. There used to be way back in the day, but no longer. Anywho, we'll spend these 3 days that we do have all on waves. Electromagnetic waves, i.e. light. Light is an electromagnetic wave. Electric fields. Magnetic fields. And they're waves, so they wiggle up and down. So light is a electric field and a magnetic field that's doing some up and down motion, and we'll learn about that. I wanted to do AC circuits again. I made a whole PowerPoint on it. Spent a good while on it. It's very pretty. I'll send it to you. Do what you want with it. But we just don't have time. It's very sad. And as far as I'm aware, I think I'm a bit ahead of the other teachers. So that's it. Like, there's just so much to cover. Anywho, make sure you all know about oscillating things. Make sure you all know how to do this and this. Specifically, we derived a rotating object. That is something that will be useful for you to know. You know, hint, hint, nudge, nudge, all that jazz. We won't be doing AC circuits at all, sadly. Yeah, very sad. I know they're important, but the logic here is if you need to know AC circuits, they'll show up in later classes, whereas electromagnetic waves, there's something that you probably might not see too much, but it is important for y'all to know that light is a wave. It explains like how all light behaves. If you don't understand that light's a wave, you can't really understand anything about light. Other than I turn on stuff and it makes light and I can see things. Like that's as far as you can kind of understand. So that's why we'll spend the time on it. And it also gives us further reinforcement of harmonic motion. Waves is something that you all need to be. Frequencies, all that kind of jazz. My gosh, they're important. One day I'll convince you. One day someone will convince you of that, if it's not me. All right, then we talked about, did all that. Then we did Lenz's Law, and we had a fun time with this. And Lenz's Law was basically, am I gaining or losing? In what direction? Oppose the change. What current makes that happen? So we practiced a bunch of those. Did a whole bunch of them. Am I getting more field lines or less field lines? In what direction? If I'm getting more, I'm going to make some in the opposite direction. If I'm getting less, make more in the same direction. And then we do right-hand rule 2.5 to find the direction of current to satisfy that. All right, then we did a bunch of more. So much practice. We did this sliding rod, and we did this cool problem that had a bunch of steps, like the falling rod. Didn't end up solving the whole thing, but it was all set up here for us to solve. So this is the rod that's falling. This is not free energy. There's a force that opposes this. And great. All right, so now we just got one tiny little thing left to do. Yeah. Does the what?
Does the falling rod oscillate?
No, it's a good question. Does this oscillate? It will not oscillate. So I do a terrible job of demos. I recognize that. Most other classes, they actually do like visual things. I don't. Probably should. Thursday, I am going to try to get something to show you all. This class size, I can actually do it. So what's going to happen is this will fall, and it'll get faster and faster, but at some point it'll reach what we call like a steady state, meaning it's traveling at a constant velocity. So that's what we found here. So the answer is it just eventually reaches some steady velocity, and it's really slow. It's much slower than you expect. You drop an object, you expect it to fall really quickly and get faster and faster. The demo that I'm going to try to bring in, it's really simple, and you can actually do this at home. If you have a metal tube, just drop a magnet down it. And what's really kind of wild that happens is that magnet will fall really slowly. Like it's going to look really odd. It won't stop, but it'll fall really slowly down that pipe. And the reason is it's a little different than this, but it's basically the same idea. So just to kind of show you all this, because it is a really cool little problem. So if I have a metal pipe, boom, there it is, and I drop a magnet through it. So let's draw this magnet like a north and south. As that north end gets closer, which way do the magnetic fields point to the north end of this magnet? Away from it or towards it? Great. So they're going to point away from it like this. Now, as they enter this pipe, you all can think of a pipe like a bunch of coils of wire stacked on top of each other. Just all connected. A bunch of coils of wire stacked in each other. They would eventually turn into a pipe. Sounds silly, but it's a good way of understanding this. So as this falls, let's say it's down here now. And let's say we're looking at some loop here. If we broke this into a bunch of loops, as it falls, do I get more of those field lines or less of those field lines? As it gets close, compare the two situations. The magnet started way up there, and now it's way closer. Did I get more down or less down? More down. Is it going to like that? No. What's it going to do to counteract that? It's going to make field lines up. How does it make a field line up? It makes a current in this pipe that actually goes around it. You can't it's not going to electrocute you or anything. You can't really see it or feel it or anything. But the net result of this is it makes a magnetic field line up. If I have two magnetic field lines opposing each other, they repel each other. So what ends up happening as this magnet falls is it's getting pushed by a current that's made in the pipe, and it slows it down, which is kind of wild. This is super easy. Like literally you just need a metal pipe and a magnet and you can see this. And it's a really cool thing to see. And I'll try to, we have a big old metal pipe in the demo room, so I'll try to get it at some point. As it'll reach some steady state. It'll reach some, so just like this last problem, basically this thing will reach some max velocity such that the force of gravity and this magnetic force are exactly equal and opposite. That doesn't mean it stops moving. It just means it stops getting faster. So it'll basically fall and then it'll kind of reach some steady state. And there's a bunch of really cool videos of this, of people dropping giant big metal things near magnets. And what basically they'll do is they'll fall and then all of a sudden they'll like slow down and then slowly kind of like fall the rest of the way. I'll try to find some of those. They're pretty wild. It's very weird. Stuff that you don't expect. Fun fact, this is how regenerative braking works. Regenerative braking works in the same way, where they just put a magnet near your car tires spinning. When they do regenerative braking, they basically just like, I don't know if there's a physical movement, but it uses this idea that this changing flux results in a force, and that's actually what slows down your car tire. But beneficially, it makes electricity, so you can kind of get some of that rotational energy back, which is cool. It's a little tricky to explain, but yeah. Anywho, Thursday, or maybe even during this class, I'll run over and grab things if I can. We'll see. They tend to not like when we come last minute, so that's why. Maybe not today. Anywho, cool stuff. All right. So we chatted about this falling rod / sliding rod. Now, something that's cool is you didn't actually we needed a loop to make a current. But the reason we did this problem is, one, every physics class does this problem. I kind of know why. It's called a toy problem, meaning it lets us see the physics, but it's not a real. No one's doing this in the real world. Now, there is an example that is done in the real world. Kind of, sort of. I got a rod. There's no longer a wire connecting the two ends. It is literally just a metal rod. I don't care what this metal is made of. It could be aluminum, copper, steel, iron. It doesn't matter. I got a metal rod moving to the right in a magnetic field. What happens to the electrons? So all I need to remind you all of is that metals, every material, has electrons in it. Why? Because they're made of atoms. Atoms have electrons. And if the rod is moving to the right, what are the electrons also doing? They're also moving to the right. I've got moving charges in a magnetic field. What will be the direction of the force? And it's very important that you realize these are electrons. See if y'all can parse this out. And while you do that, maybe I'll go run over and try to get the tube. BRB. Yeah. All right, I'll go see what I can wrangle. Try to figure this out. Are they pushed up, pushed down, and nothing happens? Okay.
So the magnetic field is being generated by some
All right, give you all about 10 more seconds. This is, do you know how to do right hand rule number 1? It is a very, yeah, it's actually better if it's smaller. It's cool to look down it. And if you say that you have to be taller to look down it. You know, just barely tall. But whatever, it does the job. It is cool. All right, 5, 4, 3, 2, 1. Ciao. All right, right hand rule. Fingers in the direction of motion. Remember, it's a cross product. When we're doing this right hand rule number 1, we're finding this, the cross product of V cross B. Fingers in the direction of V, swing them towards B. So my charges are moving to the right, so I point them to the right. I know this is, again, this room with the multiple projectors really makes the thing. It's great to have multiple projectors, but great. Fingers in the direction of this, I gotta swing them towards B. B points into the page, so this is not good. I can't swing my fingers backward. I mean, I can, but most people can't. My fingers spin really nicely. Whatever. You do it this way, and you get up, and then that's the wrong answer. Because they're negative charges. Rule of thumb, everything I teach you in this class, if I teach you something and there's charges, I'm teaching you what a positive charge does. What does a negative charge do? The opposite. Always, always. Like every single thing I've taught you, even voltage, which isn't even a vector. Voltage even is negative around a negative charge, and it's positive around a positive charge. Everything's opposite, even the scalars are. So, the negative charges get pushed down. The positive charges get pushed up. Now, the positive charges can't actually move. Those are the atoms. I'm not literally deforming the rod and moving protons. That's nonsense. But what does happen is that all the negative charges get squished here on the bottom. Why? Because they're all getting pushed down. It's a conducting rod. They're allowed to move. They all get squished here. Where do they come from? They came from everywhere. But, you know, the top part's going to miss the most of them, so it becomes positively charged. I have an area of negative. I have an area of positive. That's a potential difference between those 2 points. I have made a potential difference, which is kind of cool. And what's kind of wild is it ends up being the same math as the one that was sliding. So the problem that we did where it was sliding, we derived this expression for the voltage, BLV. It's the exact same logic. We just kind of like pretend that there's a loop there and do the same thing. So just to show you all what I'm talking about, this is the derivation for where it was actually sliding. Notice that the voltage is BLV. For this rod that's not connected to anything, it's also BLV. Now, something important here is there's no current. No current can flow because there's nowhere for it to flow. But it will get stuck there. And now we'll do quick math. Oh, before that, I did get the rod. Yay, they had it there. It was really easy. Again, this is way more fun when you do it yourself. So at some point, like during the break or clicker questions, I'll just come around. It's way cooler to actually see it, and I can't really like show you because I need it to fall. And if I do it sideways, it doesn't fall, so you see the problem. But anyway, you got the whole thing is I got 2 things. They both have the same mass. They both have the same shape. One of these is a magnet. One of these isn't. I have no clue which one's which. One of them will stick to my mug, I guess.
Well, you can just test it.
I could test it with that too, but it's more interesting to do the one that's not a magnet first because I don't know. I think this one's not the magnet. Yeah, great. Okay, look. So, you know, it fell. This is fine. Here, hold this. You can't really, the rod's really long. You could hear it, but you couldn't see it. This is fine. All right, so, you know, whatever. You stick it in there and, wow, it falls out like things do. But when you put the magnet in there, again, it's cooler when you can see down the pipe. But it takes a long time. It's a really long pipe. There you go. Now it fell out. So that's, you know, that's kind of weird, right? But it's even cooler when you see it. Because as it's going down, it's literally just like falling at this really slow rate. And it's because of the physics we talked about. But this is used for, again, regenerative braking. This is actually a fail-safe on roller coasters. Roller coasters have this system kind of in place. Because this will always work. This is not a mechanical mechanism. So roller coasters, if they want to slow you down, all they have to do is basically put a panel of metal and then put 2 really strong magnets. And when that panel of metal tries to go between those really strong magnets, the eddy currents, that's what we call these currents that are made in this, will generate and it'll slow it down. And so roller coasters pretty much all have those, and they'll work no matter. There is no physical mechanism. As long as the metal plates don't fall off the roller coaster, it'll slow it down, which is kind of cool. But anywho, at some point I'll pass this around. Again, it's way cooler to actually see it fall. That's the fun part. And all you need is a metal pipe and a magnet. You all have magnets at home. I don't know if you have a metal pipe.
Curtain rod.
Huh?
If you have a curtain rod.
Oh yeah, curtain rod. Yeah, what a great idea. Just take down your curtains. No, like seriously, I mean, it'd be fun. All right, let's go ahead and do this problem. You might be like, this is a weird problem. It's fine. I have a 20-kilometer long wire moving perpendicular to the Earth's magnetic field at a velocity of 10 kilometers per second. What's the induced EMF? You're like, these numbers are crazy. Yeah, but you'll see why. Right. Yeah, no, that's the magnet. The non-magnet's boring. It does what you expect. Yes, it's just a proof. It's so slow. It's really weird. Yeah, there was a video I watched recently. Some kind of giant hunk of metal. Dropped it. And there's one where Veritasium goes to like the Gainesville or someplace with a really strong magnet, and he takes a whole metal sheet and kind of drops it, and it just like does a really weird.
I've definitely seen the video about the roller coasters. I'm pretty sure I used that when I got this.
Oh really?
Yeah.
Oh, it's cool. Yeah, pass it around. Don't lose my magnet. This is just using the last equation. Should be pretty straightforward if you don't forget to convert your units. Convert your units. If you didn't do so, then you made a mistake.
Oh darn.
Mm-hmm.
I mean, it sounds like
This is Wix Studio, built to meet any brief.
All right, give you all about 10, 15 more seconds. I mean, this is a plug and chug situation.
yeah. But then literally on what I was like that
All right, 5, 4, 3, 2, 1. All right, so this is just really plug and chug. I want EMF. How do I find EMF for this? I just multiply the values by each other. So you multiply 5, e to the minus 5, times 20, e to the 3, times 10, e to the 3. And so I get 10 times 20 is 200. So this is actually a problem you can do without a calculator. If you know how to do scientific notation, you add up the exponents. So 5 times 20 times 10 is 100 times 10, which is going to be 100 with an extra 0. And then you add up the exponents. 3 plus 3 plus negative 5 is 6 plus negative 5. So that's going to be e to the 1. So that's going to be 10,000. Working in scientific notation is useful because it's pretty easy to like get an order of magnitude. All right, 10,000 volts. And you might be like, that's wild. That's a weird problem. That sounds ridiculous. I picked these numbers because this is an experiment they did. So they did this. Where can I go this fast? Space. So what they did is they went to space. They released a satellite with a very long wire. I think it was 20. I'm pretty sure I got these numbers from the experiment. And yeah, they generated 3.5 kilovolts between the 2 points. This voltage was so high that it actually resulted in a problem, specifically that there was a little bit of air in the insulation, and this voltage is high enough to ionize the air. Ionized air is lightning, and so it broke the wire very quickly. There's a video. You can check it out if you want. You'll see a bright flash, and that's it breaking. The danger here is that it released a lot of current very quickly, and that current's then going to, like, it did. I don't know if it results in any problems with the spacecraft. I have to check with that. It was fine, I think. But they determined that this might be a little too difficult, a little too dangerous. But it's almost like free energy. You're getting the energy from this from the Earth's magnetic field, which means that like you're actually making a force on the source of Earth's magnetic field, but the force is so minuscule compared to the thing causing it that doesn't really matter. If you saw me fiddling around with things, there's a really good, so Veritasium, I think is a great YouTube channel. He went up to, I don't know where, was it Gainesville? Yeah, state of Florida. Yeah, so I believe Gainesville, I don't want to say it's Gainesville. They're really big on magnetic fields. They can produce some really strong magnetic fields. And so they have this thing that makes a really strong magnetic field. You can check out the video on how they do it. They do lots of experiments with it. But here he's got just a giant metal thing. It's aluminum. It's not magnetic. Aluminum does not stick to magnets. This is not like one of those situations of magnetic stuff. So he just brings this big old metal plate near the thing, and then he drops it, and it just slowly falls because the magnetic field is so strong, and as it's falling, it's inducing that current in it, and that current's opposing it. But the field is so strong that, yeah, this isn't like on a hinge, or it's literally just, they just put it there and let it go, and this is what it does. So yeah, here's him standing on a thing. It's kind of, yeah, and they just let it go, and it just falls really, really, really slow. It's really surreal. It's a really odd thing to see. It almost looks like anti-gravity, but it's just from this Lorentz force, or yeah, I think they call it Lorentz force. Lorentz force caused by Lenz's law and all that kind of stuff. It does get a little warm because the current is generated in it, so that's why, like, why are they looking at the heat? Current through a thing, P equals IV, P equals I squared R. It actually generates some heat, not very much, but a little bit. Yeah, and then, you know, he tries to pick it up, and you end up with the same problem. Like, he's trying to pick it up, and it's really hard to do because as he's trying to move it, you get an opposing force due to that change in flux. It's a really cool video. Check it out. You all know the physics of it now. Anywho. Yeah, and then there's this problem, just to practice it some more. 25 centimeter rod moves at a 5 meters per second. The things are all perpendicular. Find the magnetic force on the electrons. Find the electric field. If you like electric field. How do I find the electric field? The way we're going to do that, actually do part C first. Find the potential difference between the ends of the rod. So find the magnetic force. How are you going to do that? V cross B. V sine theta. Find the EMF. And then we're going to find the electric field. We'll do part C kind of together. I'll remind you all stuff. And then the last one's pretty straightforward. But yeah, it was to show you all this, but anyway. So do part A, then do part C, then do part B. The order is not quite in the right order. And I'll put the answers somewhere at some point. Then we'll move to solenoids.
Let's see, it's just V equals E times, if we assume that the electric field is a constant. We assume that. Yeah. It's a pretty big assumption. Yeah, it's fine.
Yeah, parts A and B should be no problem for y'all. Those should be pretty quick and easy. Yeah, play with it. It's fun.
Yeah. Okay, well. I think it's I was thinking electric field constant and you're integrating GL. Isn't it probably integrating you get velocity? You integrate its position. You're right. So you get negative V. I think you just said
That's true.
you got nice professionals already.
Yeah.
They say it's just E out.
There will be an electric field.
But that's interesting because that's exactly what I got using.
Oh, you get the same number? That's
So that means BV is electric field. Right?
By the
Say
units.
too. B is a Tesla.
I don't know what Tesla is.
Tesla is something weird.
Do you want to get the answers?
So the electric field is just BV.
Oh yeah, I guess so.
Yeah, because I did this
Yeah.
this way and I got
Yeah.
the potential difference.
Yeah. If we assume a linear, I fixed it. So the order it's currently shown. Magnetic force, potential difference, and then you find electric field.
What was the other question?
Right.
What's the speed?
So for part A, magnetic force, there's actually two equations for magnetic force. You just got to choose the right one. It'll be pretty obvious which one when we write them both. Magnetic force is QV cross B. Magnetic force is also equal to IL cross B. So you just decide, which one do I have? Do I have a Q or an I? I have a Q. Something that's good to get in the habit of, it's more of a way of viewing equations. Equations are a sentence. It's kind of a weird idea, but you can read this like a sentence. This says that the magnetic force, F stands for force, B stands for magnetic. The magnetic force is due to a charge that is moving in a magnetic field. I just read the sentence, and actually I read it in the order that it was presented. The second one says a magnetic force is equal to a current, and it has to have some current with some length, whatever the material is, has to have some length, in a magnetic field. Math is a language. Equations are sentences. Each variable represents a word, an idea, a variable. Anyway, we're going to choose this one because it's a charge moving. So QV cross B, you just put the charge of an electron. You put how fast it's going. Now, reminder to y'all, this is a cross product is QVB sine theta. We're not actually going to do any cross products mathematically in this class because you're currently learning them in Calc 3 and all that fun stuff. 5 times the magnetic field, which is 0.25 Tesla, and the angle between them is, in this problem, 90 degrees. Velocities to the right, magnetic fields into the page, are 90 degrees to each other. You plug that in, and I don't know what you get. Something.
With the force?
Yeah.
2 times 10 to the minus 19.
2 times 10 to the minus 19. Not very much. Newtons. Yeah, but that's on every single electron. There is an insane number of electrons in this thing. Yeah. Is that off?
Is it positive or negative? Because it's not an electron.
Oh, positive, negative doesn't matter. That just tells you the direction it's going to go. That's a good question. Wait, was the question about the answer? Yeah, that's a good question. We don't care about positive, because what does a negative force mean? What does a positive force mean? It actually means the direction of the force. You're not going to get that from the math, at least not in this case, because we didn't actually do the cross product. So yeah, here you plug in the magnitude of it. Now, which way will that force be? You got to do right-hand rule. Bunch of negative charges moving to the right, and a field is pointing into the page. So the force is going to be down. So this will be a force downwards. Now you'll be like, oh, the negative in the problem gave me that. We just got lucky that that worked out. I can easily give you another problem where that negative doesn't work the right. So you can't actually do that. All right, part B. You all also already did this. Remember, EMF is basically voltage, so it's just BLV. So you just do 0.25 times the length, which is also 0.25 times 5, which equals another number that I don't know.
0.3125.
Point.
Oh, sorry. Yeah, that's right.
1325?
3125.
3125. Great, there's my voltage. Part C, the electric field, we're going to do something, we're going to assume. So if you all remember from way back when, V equals the integral of E dot dl. This is like a definition from test 1. We're going to assume the electric field here is a constant. Why? Because you can't really solve it otherwise. So we're just going to turn this into V equals E times L. E is a constant. What's the integral of dl? It's L. And then you just solve for E. We're making an assumption that the electric field is a constant inside this. That the accuracy of that I can't really speak to. I'm not going to have you do this on the test, find the electric field in the rod. I'm not going to have you do that. But just to connect the ideas together, the magnetic field makes an electric field inside the rod, which is kind of cool. Kind of interesting. And, you just rearrange this. E equals V over L. And you get 0.3125 divided by the length. And, that gives you another number. 1.25. Which, funny enough, it just cancels out the L from previously, so it's just 0.25 times 5. You can kind of see that for yourself if you want.
Can't you also do over 2?
Oh, yeah, that was the other way I wanted to do that. I always forget about that.
Yeah.
Yeah. There you go. Tyler reminded me there's another way to do this, which I should have remembered.
Well, force is equal to charge times electric field, so you can solve for the electric field by just taking the force we calculated in part A and dividing by the charge of electron.
Yeah, if you're like, what's he talking about? Remember, F equals, where I always, E equals F over Q. That's a definition from test 1. Hey, we got F, we got Q. If you divide it, you get the same answer. Cool, right?
So the magnetic field and the induced electric field are always equal.
They're not equal in this case. The magnetic field is 0.25. My electric field is 1.25. So anyway, yeah, that's why part B. I forgot that order of it, but 2 ways to the same thing. All right, great. We're done with Faraday's law. Now we're going to do inductors, and I'm going to tell you all for inductors, I currently only have like 2 questions on the test for that, so it's not going to be an emphasis, but it is something we need to know. We need to know, an inductor is just a solenoid that's in a circuit. We'll see that in a little bit. It is an important circuit element, so that's why we're going to actually talk about it. Ideally, I would talk about AC circuits with it, but, You can't do it all, I guess. So yeah, on to inductors, which I believe the slides should be posted. It should be. Yeah, great. So yeah, inductors are just a fancy way of saying a solenoid in a circuit. Yeah, the slides say inductors and, because they used to be inductors and AC circuits, and then I split off AC circuits, and then I decided today not to do AC circuits. Again, if it's any consolation, I spent a bunch of time making the AC circuit slides, so yay me. I'll still post them. They're cool, right? I like them. Inductors and nothing. All right, so we'll see what we can get. We're not going to go through the full thing today. I mean, it's only 20 slides. I don't know. We'll see what we get through. I'll kind of feel it out. Remember, this is the last PowerPoint slide we need to go through before the test. So it's just whether or not we have less time today or less time Thursday. All right, inductors. Great. You need to remember about magnetic fields. Shocking, right? Crazy. Sources of magnetic fields, magnetic flux, Faraday's law, all those good things. All right. Yeah, and then there's just kind of a couple things we're going to talk about. We're going to find what the inductance is for a cylindrical solenoid, and we're going to explain how energy can be stored in a magnetic field. There's a chance, there's something I didn't include in here. There's a chance I might include, it's probably, no, I'm not going to. I will probably talk a little bit about how transformers work, but I'm not going to test you all on it. So it's not currently in this slideshow, but a transformer is just two inductors connected. So, all right, great. This is the definition of self-inductance. It's just a definition. It tells us the property of a device that describes how effective the device is at opposing a change in current. So the voltage generated by an inductor is equal to its inductance. So the symbol for inductance is L. I'll add that here. So I have the unit as a Henry, which is a funny sounding unit because it's named after a guy named, his last name was Henry. So that's how it goes. Yeah. If you discover something, you get to have units named after you. But the symbol for inductance is L. This is very unfortunate because we use L for length. So now it gets to be used for two different things. And unfortunately, they sometimes show up in the same equation. It's we'll use lowercase l for length moving forward, and we're going to use capital L for inductance. I don't make the rules, I just teach them. Why is the symbol for inductance L? I have no clue. We can't use I, that's taken for current. So I don't really know what other choices there are. So they just chose that. I don't know. There's a history. So the unit is H, but in the equation, inductance will be L as a symbol. So let me write this out. So say I had an inductance, L, that would equal 5 henries. So one's the unit, one's a symbol. Yeah. Neither one's intuitive, but units are named after people, so none of them are intuitive. Think of newtons. Have y'all noticed most of the units in this class have some weird name? Ampere. We had resistance was ohms. Gosh, what else we have? Volts is named after a guy, Volta. Electric field didn't even have units. It was made up from other units. Magnetic field is Tesla. Almost every single unit, every new variable I taught you in this class, the unit's named after someone. That's how it goes. Because they were discovered in the last 200 to 300 years, and we decided in the last 200, 300 years to name units after people. Newton, so on and so forth. All right. Something interesting. Every conducting object will have some impedance, which is kind of a wild idea. Just like every circuit, every piece of a circuit has a resistance. Every piece of a circuit has an inductance. Every piece of a circuit actually has some capacitance. It becomes very messy, and electrical engineers have to worry about this. For example, in your phone, you got current-carrying wires. Those current-carrying wires might vary their current over time, which means they're making magnetic fields around them that vary with time, which means they're inducing currents in other pieces of the circuit that vary with time. So everything affects everything else, and it's actually it's a problem with miniaturization that we kind of run into. When the devices get really close, they start to affect each other a bunch, and electrical engineers have to worry about that. So have fun, electrical engineers. You'll get to learn that everything has everything. Everything has resistance, everything has capacitance, everything has inductance. And you on the big level, you don't have to worry about it, but when you get really small, you have to start worrying about that. All right. What is the rate at which the current through a 0.3 Henry coil is changing if the EMF is 0.12 volts induced across the coil? Pretty straightforward. It's just using that equation and being like, this is okay. I'm okay with this. So we measure a voltage across this. At that exact moment, what is the rate of change of current causing that to happen? Nice table. I didn't actually notice. Yeah, it's literally every single one I taught you. You gotta figure out what you're solving for. The units of all the answers give a pretty good indication of it.
Oh, yes. Oh, it's absolutely out.
So easy to make good mistakes. Yeah. We don't actually have
It resets in 2 days.
So no one's reporting Henry resistance. So inductance is like resistance. You go to a store and you bought an inductor, it would just say, and it won't be a Yeah, that's a great question. I just kind of breeze past. I'll mention it now, though. All right, 10 seconds. This is pretty straightforward. It's just whether or not you're careful in your algebra. All right, in 5, 4, 3, 2, 1. Boom. All right, so I have inductance. I have EMF. EMF, or let's write it this way. L equals EMF over di dt. Now, these are absolute value, and actually I'm going to go back and point that out because I kind of just breezed past that. But rearrange this for di dt, and that just equals EMF over L, which equals 0.12 over 0.3. Double checking that I put the things in right. That goes there, that goes there. And you should get, I'm getting paranoid, 0.4. Yeah, I'm dividing a small number by a big number, so you get even out. All right, now, something I want to point out, because I kind of breezed past this. There was a negative sign. This negative sign came from, remember, it's why is there an EMF? It's the same reason we've been talking about. Why is there an EMF? Because anytime there's a changing flux, it opposes the change in flux. That's the point here. Why do these devices have a voltage across them? They have a voltage across them because as my flux changes, I get a voltage. Now, notice that we haven't written it. These are written differently. We're going to actually use that relationship later. We're going to set them equal to each other. Right now, this is just a definition that things oppose a change in current. Why do they oppose a change in current? Because they don't want their flux to change. As the current changes, it will change the magnetic field in the thing. As it changes the magnetic field in the thing, it doesn't want that. So these devices will make a magnetic field. They don't want that magnetic field in there, so then they oppose that change and you get this voltage. So that's the idea. We're going to see it when we get to solenoids. But what I want to point out here is this is something that you would buy from a store. So just like you could go to a store and you might be like, what store? I don't actually know. Maybe Ace Hardware. You could go to a store and buy resistors. You can go to a store and you can buy capacitors. You can go to a store and you can buy inductors. And when you go to the store and you buy an inductor, just like a resistor will say 100 ohms. A capacitor will say 60 microfarad. You'll go to a store and it'll say like 3 henries or 3 millihenries. And they'll actually be labeled on the device. And it's an absolute value. You're not going to go to the store and buy anything that says negative 3 millihenries, just like you're not going to buy any resistors that are negative. You're not going to buy any capacitors that are negative. This is always given as an absolute value. But the negative sign was just because it's opposing the change in current. That was why it originally showed up here. But then we got rid of it because you're not buying negative inductors. That's the idea. I'll show you a picture of what inductors look like in a little bit. All right. Okay. This is going to be kind of a weird statement, so I need to clarify this. I couldn't figure out exactly the wording. At some point, the current through a device is 5 amps, and it stays 5 amps. So my question is, okay, I got a steady 5 amps going through a circuit. I'm going to get the inductance of the thing. At some later point, I got a steady 10 amps going through it. And I'm going to get the inductance from it. My question to you all is, if my current stays constant, what's my di dt? If my current does not change, what's di dt? I'll write that out and let you all think about it. If current is constant, in this case they're both constant. In one case it's a constant 5, in the other case it's a constant 10. If current is constant, what's di dt? Not a trick question. Give you all some moments to think about. All right. Y'all tell me, what's the answer? With confidence. Y'all, you can be confident about this one. 0. Great, right? It's not changing. Why am I saying this? We don't care how much current's going through my circuit. We care how much the current's changing. That's the part that's important here. Inductance doesn't care how much current. It cares how quickly that current changes. That's the mindset you all need to get with these inductors. These are very useful things to have in circuits because sometimes you don't want the current to change really quickly. You all can think of like a power surge where I have like no current and then all of a sudden maybe a lightning bolt strikes near your house and suddenly you have a ton of current. It might be useful to have a device that responds to that very big spike and opposes it. That's one maybe use case for these, if you want to oppose a big burst of current that kind of comes out of nowhere. And there's other applications as well. All right. So we're going to derive the expression for the inductance of a solenoid. And this is going to be a good reminder for us of a solenoid in general. So we have L equals epsilon over di dt. All we're going to do now is remember the definition of epsilon for, this is what we did in the last PowerPoint. It's Faraday's law. Remember that flux equals, and we're going to go ahead and I'm debating whether or not to put the in now or not, because for some reason I didn't have it before. But we're just going to do d flux dt for now. We're not going to put an in. We're just going to look at a single coil. We're going to assume a single coil. So that's the definition of why do I generate an EMF? Because d flux dt. Like that was what we just spent the whole last week talking about. So great. We take that, we chuck it in there. So you get L equals d flux dt over di dt. All right, great. Now we're going to do something that, again, I always say mathematicians don't like this. This is the same as d flux dt times dt over di. We're going to treat these like variables, which, again, I don't really know why mathematicians don't like it. I think it's because these are technically taken, whatever. Physicists, we don't care. We're going to cancel those. What we're doing is weird, but it's fine. If we just treat these like variables, we're allowed. At least physicists say we're allowed. Don't talk to the mathematician. Again, I don't know. Supposedly it's a thing. Great. There's the equation for flux dI. Now what we need to remember. So just write this out. D flux. So L equals D flux dI. Let's write what flux is. That's maybe useful. BA cosine theta. Again, you all don't need to derive this. I'm just doing this to show you that what I'm about to, the final result didn't come out of thin air. Every step here is a step you all can do. You all know that EMF is change in flux over change in time. Then just some algebra. You all hopefully know that flux is BA cosine theta. Now, this is a solenoid, so something we haven't really messed with solenoids too much, but it is in our formula sheet. There is a formula for the magnetic field in a solenoid. We derived it before. The magnetic field in a solenoid is mu naught in I, or if you want to write it this way, mu naught in I over L. That's the length. So that's just an equation on the formula sheet. I think I gave you the one on the right, but they're both the same thing. Little n is capital N over L. It's the turns per length. So that is just the equation for the magnetic field due to solenoid. I didn't come up with that out of thin air. We're just going to take that and chuck it in there. So we're going to take the magnetic field of a solenoid, pick our favorite one. I don't really care which one. Let's do this one. We're going to take that and we're going to put it right there. All right. And now I see it actually might have been easier to explain this before. Just to make my life a little easier, I'm going to chuck in some ins. I could have done it later, but in. This will just make my life a little easier to explain. That was the definition I gave you all before, so great. It's there now. Chuck this in there. So L equals N times D mu naught in I over L times the area times cosine theta over DI. And you may look at this and be like, oh my gosh, so many things. N is how many loops. I is the current. Well, let's just be now. L is the length of it. I'm going to make that a little bit easier to read. Just taking things and plugging them in. L is a constant. It's the length of my solenoid. We're not taking that solenoid and stretching it. N is the number of loops. That's a constant because we're not adding more loops. A is the area of the solenoid. That's a constant because we're not stretching the solenoid. So everything's a constant. Oh, look, but there's an I. What's the derivative of I with respect to I? It's 1. So just pull and the angle here between these is 0 degrees. So the angle with the magnetic field and the area vector, those are lined up. So that angle is 0. So this ends up being really simple. We get an N, we get a mu naught, we get another N, we pull out the L. I'm just literally just pulling everything out, and I'm just left with DI over DI. And today we did it. That's the expression for the inductance of a solenoid. Every step here wasn't too crazy. It was just plugging other equations into other equations and doing algebra. And yeah, there it is. That's the equation for the magnetic field due to a solenoid. Mu naught N squared A over L. Fingers crossed I did it right. Yay, I did it right. There's it nicer. It was a little different. I put the ends down there instead, but it ends up the same. Boom, there it is. That's the one we just derived. The difference between these, all we did here is remember that N, lowercase n, is capital N over L. So you all can do the algebra to prove that those are the exact same thing. Capital N squared, there's an L top. So this is the equation for the inductance in a solenoid. This is how much a solenoid opposes the change in current, and it's purely a geometric and material property. How many turns? What's the area of my solenoid? How long is my solenoid? And we're not going to worry about it for this class, but if you do put an iron core in the solenoid, it does boost the performance, but we're not going to get into it. It changes mu naught to mu. Just like when we have a capacitor, you could change what's in it to boost the performance. You can boost the performance of of a solenoid by putting an iron core inside it, or some other conductor. But yeah, think of it like it's purely based on how the thing's made. That's why you can go to a store and buy a 5 millihenry inductance. It's just literally how many coils did they do, what's the area, what's the length, math. That's it. And so this is nice. Yeah, it's really hard to make a 1 Henry solenoid, just like it's really hard to make a 1 farad capacitor. That's a pretty common trend in these. It's just how the units work out. So here you go, solenoids. We just call these inductors. When you go to a store, you'll just buy an inductor, and it's a solenoid. They won't tell you it's a solenoid, but it is. Here's what they look like. There's a whole bunch of them. So some of them kind of look like a solenoid, but it's just kind of bent back on itself because it takes up less space. If you're like, what is a solenoid? He keeps saying the word solenoid. This is a solenoid. It's a slinky. If you just take that slinky and bend it on itself, it's still a solenoid. We can pretend like it is. Technically it becomes a toroid, but don't worry about that. And they have various different types. Do I know much about those? No, I don't. No, not at all. But those are all different. If you've seen a circuit, anything that looks like any of those things, it's an inductor. It's a solenoid. And there's some kind of funky looking ones over here on the right. These like little boxes. Do I know what's going on in those boxes? No, I have no idea whatsoever. But they function in this way. I do know how they function. So, fun fact, wireless charging, it's a flat solenoid. It's not really a solenoid, but it's a bunch of loops of wire. Yeah, I actually don't know why I didn't mention this. How does wireless charging work? It's what we've been learning about. You just got a loop of wire, you put it on top of another loop of wire, you put a changing current in that bottom loop of wire, that makes a changing field. A changing field in your loop of wire makes a current. Yay, wireless charging. Wireless charging is also Faraday's law. So, which most people have no clue how wireless charging works. Now you do. Have fun trying to explain to people, and then they'll be like, I don't get it. Because you have to understand Faraday's law, and that gets a little, funky. But yeah, this is what wireless chargers look like. They're literally just a bunch of wires, and that's just to boost the magnetic field. Wireless chargers also get hot because they got to pump a bunch of current through those things. If you want to make a strong magnetic field, you need to pump a lot of current through those wires so they get warm. This is also why the wireless charger has to be super close to your phone, is because magnetic field strength drops pretty significantly over distance, so you need it to be really close so that the flux is as maximum as possible, the change in flux. So, fun things. All right. Just to prove to you, hey, there's a solenoid. There's how long it is. There's how many turns it is. There's the radius of it. Find the inductance. I didn't tell you what the rate of change of current was. I didn't tell you what it was connected to. It's purely a geometric quality of the material. Material as well, but we're not going to get into that. Math. Oh yeah, and that was the only equation you basically need to know in the entire PowerPoint. I guess that one and the definition of E equals L di dt. Only 2 equations in the entire PowerPoint that you need to know. But y'all can see here, this is pretty hard to make. Like 500 turns, that's a lot of turns. Doesn't make that big of a difference. And no one's building 50 centimeter long solenoids. Yeah. We love our circles. Circles are much easier to wind a coil around than a square. That's really what it comes down to with it. You just put it on a big thing that spins really quick. Yeah, that's it. Yeah, if you want to make these things, hook it up to a drill or something. The area here is a circle. I didn't specify that, but that's a solenoid. Is that slinky kind of looking thing? It's a circle. You haven't memorized the area of a circle yet? Gosh, you've used it so many times. The best. We love circles and spheres. Best shapes.
If you have your keys, we could pull them out.
Yeah. I wish I could get rid of some of those, but like every one of those keys has a purpose.
Just in case.
Yeah, I could get rid of one of them. Or they moved the printer room. Yeah. Car keys, house keys, room keys. Yeah, bigger one. It was pretty chunky as is. Look at that.
There's a long one.
Oh, so nice. It's so sad to not see circles. Phasor diagram.
I looked at the PowerPoint. I think we were gonna get into it. Yeah, it was good. You did a good job.
Found the
I
cool
enjoyed it.
imaginary, found the imaginary reel, and the reel's a projection on it. Yeah. All right. 20 more seconds. This is just can you chuck variables into an equation? Convert your units. You know, don't forget to do that. The real world's not always in meters. In fact, it rarely is in meters. No one's building solenoids with meter size radios. All right, I do see some people calculating it, so I'll give you a little bit more time. But this is an exercise in plugging it into the equation. Did you check the answer sheets? Okay, great.
Yeah.
These have been used in the past, so I was pretty confident they should have. But when I first made these a time frame ago, there were ones that didn't have right answer.
I'll double check.
All right, 5, 4, 3, 2, 1. All right. Now, so self-inductance, there's a reason we call it self-inductance. The weird thing that's happening here, so up to this point, I've told you something can't affect itself, but clearly this word has the word self inside of it. The reason that the solenoid can affect itself is it's not affecting itself. If you all think of this like a bunch of coils, it's one coil affects all the other coils. That's the logic here. So it's not like, that's why it's called self-inductance, because it actually does affect itself. And the reason it does is because this is not just one wire. It's a bunch of loops of wires. So each loop affects every other loop. That's what's going on here, just to clarify that. I've got 500 loops of wire. Each loop affects every other loop. Anywho, that's just an aside, but the equation here is pretty straightforward. You got the mu naught n squared a over L, and you got the mu naught n squared AL. And then we just look at what we have. We have capital N, we have length, we have radius. Remember that the pi r squared. Why? Because it's a circle. And then you pick the one that we can do. We pick the one that's got capital N and L, because that's what's given in the problem. So L equals 4 pi e to the minus 7 times 500 squared times pi times 0.02 squared all over 0.5. Now, pro tip. I've seen quite a few people. I will see people plug each of these steps in one at a time. just plug this entire thing into your calculator. Don't do it in steps. Every time you have to plug something in your calculator and hit enter is a chance for a mistake. Do it one time. And when you plug that entire blob in your calculator, you can check that the blob you plugged in is the blob that's written on the paper. It's a really great way to check your work. Every time, the more times you plug it in, gosh, it's so hard to check your work and make sure you didn't fat finger the wrong number. It happens. So just plug this entire thing in. I'll type it out. When I get my calculator, I'm not going to do it in pieces. I'm not going to do the top and then divide it by the bottom. I'm just going to type the whole thing. So I'm going to do 4 pi e to the minus 7 times 500 squared times pi times 0.02 squared divided by 0.5, and then I'll hit enter. One big blob. I checked my calculator. I checked that. They look the same. Good job me. I didn't hit the wrong buttons. And I get 7.89 times 10 to the minus 4 Henry. It's hard to make a big inductor, y'all. This is a pretty big area. You might not think a radius of 2 centimeters is that large, but you're not fitting that in a small circuit. That's like, it's pretty big. Gosh. It's kind of like this thing. This is like chunky. This is about, this is actually half that radius or so. So it'd be like twice the radius of this. And it would be 50 centimeters long, which, that does actually lower the inductance. So, if we made that smaller, that would make it an order of magnitude larger. What else do we have here? Number of turns. Yeah, they really cram these turns in. Just to show you all something, this solenoid that I'm holding in my hand, it's kind of orange. That's because what they do is they take these wires and they paint an insulating material on them. These wires are not covered in rubber. Why? Rubber takes up a lot of space. You know what doesn't take up a lot of space? Paint. Specifically an insulating paint. It's not like paint on your wall, but it's the same idea. They coat it in a material. They can even
It's good for temperature resistance too, rubber.
Oh, go ahead and explain why. I don't know.
Also, the paint is better for resisting temperature. Like in case you mess up your circuit and it gets really, really hot, rubber can melt. The paint is withstand pretty high temperatures.
Yeah, and I don't think they do this, but you could even oxidize these surfaces, and rust is a good insulator. It's an okay insulator. But yeah, this is some coating. I honestly don't know what the hell they do the coating process, but it's very thin. And that lets me jam a bunch of wires in here. That's the idea. The more wires you can jam in the same space, the better. All right. Now, classic, right? I change a bunch of things. What happens? So what happens to the inductance of a solenoid if I double the number of turns, double its length, double its radius? Don't be tempted just to multiply 2 times 2 times 2. Actually use the equation, because you got to actually know, are they on the top or are they on the bottom? Are they squared or are they not squared? Look at the equation, plug in the change. If it's squared, you better square that change. If it's on the bottom, you better divide by that. So yeah, do I get 1/4 the inductance, 1/2 the inductance, 4 times the inductance, 8 times the inductance, 16 times the inductance? You do not want to do this in your head. I don't want to do this in my head. Write down the equation, plug in the changes, do all the squaring stuff, pull it all to the front. Do not try to do this in your head. It is folly. Huh? Yeah. Great, so do I. They're so easy to make. They really test it. Yeah, it's so nice. So these are the ones. Oh, and if that's clear, these are the type of problems you need to be prepared for the test if you haven't already realized that.
Not yet.
Oh, they're so easy to make. For me, at least, they test if you understand the equation more than anything. I don't know. I think they're useful practically. I think it's useful to
Probably good if you're prototyping.
engineer. I think so. I haven't done much engineering myself, so I don't know
It makes sense.
Often the equations are actually used. A lot of the stuff they have to do numerically. It's actually too complicated for an analytical solution.
But it's also good for like organizers.
Yeah,
It's
yeah.
like, oh, I
I was
need
gonna
double
say
the
that.
power. Yeah, I do.
Just for like a rough.
Or bank on. Again, I haven't done the engineering, so I don't actually know.
Yeah. The funniest in lab thing that I remember was like, we like tested this works is we like build this metal plate. We literally just print out of our like 2-scale model that we made like in like the SolidWorks and printed with piece of paper and like stuck it up for like the boards. That was expensive. Not worth
I know it too. I was like, you know what? I think my once. Yeah. I really want to go. I just hired Yes, you told me how you went. And you had someone gave you a tour. She was like, so I was at that, but yeah, great tour.
Well, I guess it's also
Yeah. Just start spraying everything.
That are just circling around.
Oh, I'm so anxious to get my test for that. She said tomorrow I will get actual tests. So it's so bad.
the test had this APR at like 1 o'clock.
Oh, really?
Yeah.
Good.
All right, 20 more seconds.
I'm really looking forward to that. I usually just keep off the lowest one.
All right, in 5, 4, 3, 2, 1. All right, so the trick to this is we always write the equation. Again, doing it in your head is silly. Smart people don't do things in their head, which is like a counterintuitive statement. You'd be like, oh, but if they're so smart, they can do it in their head. Yeah, that's how you make mistakes. It is. I guess a better way to phrase that is it's not wise to do all this stuff in your head. The only benefit is you might make people think you're smart, but they won't think you're very smart when you get it wrong. It's far better to get an answer right than to make other people think you're smart. All right, great. So we got the two equations, and you're going to pick the one that makes sense. We don't have turns per length. We have turns. We're going to pick the first one again. And then you put the changes in. Mu naught stays the same. In, that's getting doubled, but it needs to go squared, so we put that in parentheses. My area is pi r squared. My radius got doubled, so I'm going to put that in parentheses. My length, that also got doubled. 2 squared on top, another 2 squared on top, a 2 on the bottom. So I pull out a 4, then another 4, then a 2 on the bottom, and then the top is everything left over, which is the OG. And so you can see here, 4 times 4 is 16, divided by 2 is 8. This is a back of the envelope calculation. It's a quick thing. but it's very useful to write out because once you start to have multiple things going on, it's a pain. Now, I was walking around and a student mentioned something else kind of interesting. He mentioned that, again, just to convince you all that inductors are important. Actually, let's just look up a 2 Henry inductor. 1 Henry, 2 Henry. Let's see how big they are. Oh, these aren't that big. Let's see. Let's go to a random website. This will be good for us. I don't know how big this is. All right. Now, you do run into, so the student mentioned a welders actually have a bunch of inductors have a big old inductor attached to them. I've never done any welding, but so I'm speaking from secondhand knowledge here. Welding either works with constant voltage, constant current. If you want to keep current the same, so this I can speak to. If you want to keep current the same, you don't want fluctuations, an inductor is great for that. Because when there's a fluctuation, the inductor is going to oppose that. The inductor is going to cancel that out. So that's another use case for inductors. Anytime you want a steady current, you're going to put an inductor on there to help because if it starts to change, it's going to fight that. And that's very useful for a bunch of applications. Welding is one of the applications mentioned. In their case, their inductor was massive because they're working with such large currents. I put away the inductor I had. If you all try to run, so engineering-wise, just fun fact for y'all, I can't pump 1 amp of current through this thing and expect good things to happen. These wires are super thin. If you try to put 1 amp of current through this, it would get toasty. Real to like touch it and burn yourself toasty. How do you avoid that? Use a chunkier wire. So this is one of the fun things with engineering. It's not enough to just be like, oh, I want a big inductor. And so therefore, I'm just going to put as many turns of wire as I can. And thin wires are better. I can fit more of them. No, you need a fat wire for a bunch of current. You got to think about those things. That's where engineering gets really interesting. Not only do you need to think about that, you also have to think about the cost. You can't just like use any material you want. So it's just, that's where engineering gets fun. You learn the physics, you learn the all the principles, but then you actually have to apply it in the real world where money becomes a problem. Which introduces, a good engineer cannot build something with infinite money. They can build it with the lowest amount of money possible to meet all the benchmarks. It doesn't mean you're a cheapskate. You're still meeting the benchmarks, but hey, if I can build it for half the cost, then I just saved a bunch of money and it still achieves the same exact results. All right. Look, there's really not much here. We'll leave something for next class. Now, at this point, you all are still paying me, so I will stick around as long as you're willing to stick around. But I'm going to call that good for today. If you all want to work on problems or whatever, feel free to stick around, and I will stick around as well. I never want you to feel shorted. I'm getting paid the whole time, so I will stick around. But we only got a few slides. We will start the lab after we finish those slides. So we're not going to start the lab like halfway through class. It'll be like after 30 minutes or something. Go use this time to study or stay here and study. I don't really care. Just have a good one. Make sure you practice right-hand rule. A lot. All the right-hand rules.